right, here we go. Okay, the fundamental theorem of algebra today, you guys. Again, I mentioned this a little yesterday, like I just kind of briefly was like, because of the fundamental theorem of algebra, right? Throw it out there. But it's really a nice theorem, and it's one that you guys pretty much know, right? If you have a polynomial and the largest degree is 4, right, like x to the 4th plus 3x cubed plus 2x squared, blah, 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 how many solutions could you have? If it's x to the 4th, yeah, you could have a maximum of 4 solutions, right? That's what the fundamental theorem of algebra tells us, okay? That's all that this whole thing says, okay? And what it basically is saying is that maximum number is 4, but among those 4 solutions, if n is equal to 4, right, if your largest degree is 4, that there could be, some of those 4 solutions could be imaginary. They could be complex. And others could be real. So you could have some of those solutions have i's in them, okay? Others could not have i's. You could have 4 that are all real. You could have 4 that are all complex, okay? But that the maximum number would be 4. So looking at these, and again, our definition here for polynomials, right, is just looking at your exponents, right? Looking at these exponents. Where n has to be greater than or equal to 0. We can't have negative exponents, okay? And that first term can't be 0. So which of these would have at least one root? How about A, yes or no? Yeah, it's just a regular polynomial. In fact, how many roots would that one have? It would have 3 roots. Again, maybe 2 of them are complex or imaginary, but there would be 3 roots. How about B, how many roots would that one have? It would have 47 possible roots. It is still yes. Your exponents are still numbers that are greater than 0. So we're good, okay? And the coefficients just have to be any number possible. So even though the coefficient's square root of 2 or irrational pi, right, it still works. Monday, guess what Monday is, guys? Side note. Pi Day!
Are you playing Pi?
If I remember. It's a busy weekend, though, so I don't know.
I'll email you.
Okay, email me on Sunday night and be like, Pi! But you have to spell it the right way.
P.I.
That's right. All right, let me see. How about this one? Would this one be considered a polynomial?
I like apple.
Yeah.
Yeah, this would still work. Okay. Right, x squared, x to the first. Even though our coefficients are, in this case, i's, imaginaries, it still would be a polynomial. Okay. All right, linear factors theorem. Some of the stuff we're going to talk about today you guys have already heard before, okay? Basically what they say is that you have this long polynomial, that you can express it in factored form, right? So it can be factored somehow, and some of those factors might be imaginary, some of them might be irrational, but it can always be expressed written out like this, right? X minus r, x minus r, x minus r with all your roots, okay? And so our job is going to be to write them out in factored form. Well, we need to find the roots in order to write it in factored form, yes? This first one, nice and easy. How would we write that one in factored form? Can you guys factor that? Sure you can. Go ahead and factor. Or try to factor. But I'm lazy, so I'm not going to. Come on now.
Just wondering if it would be. You can't. Oh, wait.
Okay, so did we factor? Okay, what'd you get?
3x plus 4, x minus 2.
Okay. 3x plus 1 and x minus 2. So one little important thing here is that we want to rewrite this. So notice up here the format, up here, they have some a out in front. And notice all of these are just x, x, x. A 3x is not really allowed. So what we want to do is just factor out that 3 from the first term. So we put the 3 out in front. And then we're just left with x plus 1/3. You with me? Now, why is that so important? Because what we want to be able to grab from this is we want to be able to grab our roots right away. So when it's in this format with the 3x plus 1, it's kind of hard to see what the root is. Once we factor out that 3, though, it's really easy to see that our solution is negative 1/3. Okay, so that's why we want you to write them like this. Just for this, for this unit, sort of, our factored form really should just have them so that we can see our roots. And again, it does tell you here, you want that a to the n there, and it's just x minus root 1, x minus root 2. All right, do the same thing for b. You got well, yeah, go ahead and factor first. All right, what'd you get when you factored it? 2x plus 1, 3x minus 2. Very good. All right, so we know how to factor. But again, from each of those, we need to factor out those coefficients, right? So the first one, we would factor out a 3. You get x minus 2/3. And the second one, you factor out a 2. But then you have this 3 and the 2 there, so really, if we want to write it in this format, this is really the format we have to write it in. Those 3 and 2's get multiplied together, you have a 6 out front. So again, nice and easy now. We can see our root has to be 2/3 and our other root has to be negative 1/2. All right, try the last one. Does it factor? No. Multiplies give you 5, adds give you negative 4, not going to happen. So what do we have to do to solve this? Quadratic formula. Okay, so let's go ahead. X equals opposite b plus or minus square root b squared minus 4ac. All over 2a. You guys are so boring. Why are you not singing with me? Thank you, Chris. All right, what happens? Yeah, this is like, what, negative 4 under there? Yeesh. All right, so let's keep going with i's. All right, so I end up getting 4 plus or minus 2i over 2. Let's simplify that. What do I get? 2 plus or minus I? Okay, so those are my two roots. Right, and if it helps you, root 1 you could say is like 2 plus I, and root 2 is 2 minus I. Okay, so you want to, you can kind of write them like that. So what do I have to do now? I have to rewrite it in factored form. Okay, for this problem, for this exercise, we want to write it out in factored form. So that means my first term would be x minus the quantity, that first root, 2 plus I. And then the second one would be x minus the quantity, 2 minus I. That's really all we're doing. This format says that we do x minus R1, x minus R2. Okay, so you just plug them in there, and then you can simplify a little, right, with distributing. So then it would just be x minus 2 minus I, and x minus 2 plus I. You could leave it like this, actually. I would take either answer here. Okay. Questions so far?
So we don't have an A for that one.
You don't have a what? An A. That's a good question. No, you don't have an A for that one. Notice the original equation, your A was just 1. And so if that original one has a leading coefficient of 1, you're not going to have any other A to factor out. Good question. All right, we talked a little bit about multiplicity yesterday, right? Every polynomial equation of degree n greater than 1 has exactly n roots. We talked about this, right? Even if it's a multiplicity root, you would count the multiplicity to count each of those roots like 3 times or whatever it needs to be. Let me show you what I mean here. So for example 3, they want us to find a polynomial with a leading coefficient of 1 such that the equation f of x equals 0 has only those roots specified below. So for the first one, we want 3 roots. No, that's not what it means. The root is 3, got it, and it has a multiplicity of 2. So how would I write that polynomial? X minus 3, but multiplicity of 2, x minus 3, okay? What's the degree of that polynomial? 2, right? And if you work this out, you would get what? X squared minus 6x plus 9? Okay, so that would be my polynomial. How about for this one? If I have a root of negative 2 with multiplicity 1, it would just be x plus 2, right? What's its degree? 1. And how about a root of 0 with multiplicity 2? X minus 0, otherwise known as x. That works. So if you think about it, it technically is x minus 0 squared, which would just be x squared. What's its degree? 2. So if we wanted a polynomial that has all of these, right? I would just have to take all of these together. So I'd have the x squared minus 6x plus 9. I'd have the x plus 2. And I'd have the x squared. And then what would be my total degree? Right? I would just add those up. So 5 should be my total degree. Right? Which makes sense. Okay. And then we could leave it like this for now. If they asked you to write it out in factored form or in standard form, you could change your answer if you needed to. All right, makes sense with the whole multiplicity thing. Nice and easy today. Turn the page. Next page. Did I hear? Wait. No. No. Okay. All right. Find a quadratic function f that has zeros of 3 and 5, and ooh, I like this one. All right, quadratic function. So if I'm going to write this in factored form, let's use the format that we just saw on the other page, which was like some a out in front, and then x minus root 1, x minus root 2. Well, we know those zeros are 3 and 5, so we can plug those in. So we have x minus 3 and x minus 5. All right, now what do I do with that other information they gave us? It passes through the point 2, negative 9. What do these represent? What variables? X and y, or x and f of x. Agreed? So what I'm trying to figure out is what is a. That's my question here, right? So I can use the 2 and negative 9, plug those in for x. There it is. And y. And can I work this out? All right, we've seen a problem like this. It's been a long time though. So what does a equal? Negative 3? This would be positive 3, divide. And so then when I write my final equation, and it doesn't say if you have to write it in factored form or standard form. So if it doesn't say you have to do standard form, I would just leave it in factored form, right? Why make more work for yourself? Okay. If it did say standard form, you would just distribute everything out. Easy enough? All right. Use the information you're given, plug stuff in, and solve. A lot of this stuff, this chapter, is really reading the question. How do they want you to format your answers? Okay, what are they asking you for? Just make sure you're really reading carefully. All right, this chart I feel like we've seen before, but I want to see how many of you remember it. Okay, it's been a while. You guys remember this? It was something about R1 plus R2 and R1 times R2. The product and the sum one. Yeah, something about a product and a sum and blah, 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 blah. Okay, so let's do the first couple and see if you guys remember what it was. Anyone remember it? R1 times R2? Or R1 plus R2? Does anyone remember what that equals?
Negative b.
Negative b. Look at you, memories. I love it. And how about R1 times R2? C. That's right. Yes, that's what you were going to say. All right, for those of us that did not remember it, this is the product and sum theorem for quadratics, right? So let's factor this. We got x plus 2, x plus 1. So what is root 1? Negative 2. What is root 2? Negative 1. What is R1 plus R2? That's negative 3. What is R1 times R2? 2. Where do these numbers come from if you look back to the original? Remember now? So notice this original, b was equal to 3, so this is equal to negative b. And notice in the original, c was equal to 2, so this is equal to c. Do you remember this? A little bit. It's kind of briefly coming back to you. Okay, so this is all review. Again, you can do the same thing here. What would this mean? Negative 3, negative 2. So 3, 2. If I add them together, I get 5. Oh, look at that. That's the opposite of b. And if I multiply them, I get 6. Oh, look. That's equal to c. It'll work every single time. We get the idea? Do I need to do the whole chart?
No.
All right, you guys, you get the idea, right?
Yeah.
And then you'd have 5 and negative 2, and that would be what? 3. Look, it works. Opposite of b, right? And 5 times negative 2 would be negative 10. Oh, look, it's C. Okay, so you guys get the idea. If we jump down to sort of in generic form here, sorry, video paused on me. If we look down to generic form, if this is R1 and this is R2, then we know that R1 plus R2 is always negative B, and we know that R1 times R2 is always C. Okay? All right, so how can we use that in these problems? On example 5, suppose the roots of the quadratic are 4 and negative 5, and the leading coefficient is 1. Write an equation that fits these specifications 2 different ways. So the old way to do this, right, would be, writing them in factored form, which is what we just did on the page before. So we'd write f of x equals, it said a is equal to 1, x minus 4, x plus 5, and then we'd work this out. You get x squared plus x minus 20, right? So you can do it that way. Hi, who do you need? Yeah, Jose, just go in the hall for a second. Using this new, not really new because we actually did it before, right? But sort of new, sum and product theorem now. Well, if we know that R1 plus R2 has to equal negative B, we could just plug those in. And so what does B equal? B should be positive 1, right? So we would change the sign. And then R1 times R2 is going to be C. So 4 times negative 5. So C is just negative 20. And then I just write it. Leading coefficient is 1. My B is 1. And my C is negative 20. All right, so is that easier? Is it harder? I think it's a little quicker to use this way, but again, you could obviously FOIL stuff out if you want to. And remember with these ones with the R1, R2, this sum and product formula, it only works if you have a leading coefficient of 1. Okay? So you can only use these when you have leading coefficient of 1. All right, I'm done. Questions? All right, so if you didn't finish practice packet, I'd say go back and finish practice packet page 1. Otherwise, you can start working on your homework.
Yeah.